A spacecraft racing past a lumpy, peanut-shaped asteroid at more than 30,000 miles per hour captured just a few minutes of close-up data. Months later, when scientists finally finished analyzing what that brief flyby actually recorded, they published their findings in one of the most prestigious scientific journals in the world, revealing a level of geological complexity nobody expected to find hiding on a rock most people had never heard of before that moment. We are talking about NASA's Lucy mission and its genuinely remarkable flyby of the asteroid Donaldjohanson, a rehearsal encounter that turned out to be far more scientifically significant than anyone originally anticipated. If you have not been following Lucy's journey through the solar system, stick around, because this mission represents one of the most ambitious asteroid exploration efforts NASA has ever attempted, and it is only just getting started. Let's back up and understand exactly what Lucy is actually trying to accomplish, because the scale of this mission's ambition genuinely sets it apart from almost anything that came before it. Lucy launched in October of 2021, embarking on an extraordinary 12-year journey covering more than 4 billion miles, all in pursuit of a single groundbreaking scientific goal: studying the Jupiter Trojan asteroids, two enormous swarms of ancient space rocks that share Jupiter's orbit around the Sun, one cluster trailing behind the giant planet and another leading in front of it. Scientists believe these Trojan asteroids represent some of the oldest, most well-preserved leftover material from the earliest days of our solar system's formation, roughly 4.5 billion years ago, making them genuinely irreplaceable time capsules for understanding how our solar system actually came together in the first place. Lucy is named after the famous 3.2 million-year-old hominin fossil discovered in Ethiopia back in 1974, a find that dramatically reshaped scientific understanding of human evolutionary history. NASA chose that name deliberately, drawing a direct parallel between how the original Lucy fossil revolutionized our understanding of where humanity came from, and how mission scientists hope the spacecraft will similarly revolutionize our understanding of where our entire solar system came from. Before we go further, if ambitious, multi-year space missions like this one genuinely excite you, go ahead and tap that like button right. Now, it really does help this video reach more people who appreciate this kind of long-term scientific commitment. Over its full 12-year mission, Lucy will study more asteroids up close than any single spacecraft in the history of space exploration, ultimately visiting 8 different asteroids, including several binary pairs with small orbiting companions. But before Lucy ever reaches its primary Trojan asteroid targets, its journey takes it directly through the main asteroid belt, the vast region of rocky debris, orbiting between Mars and Jupiter, giving mission scientists a valuable opportunity to test the spacecraft's systems on real targets well ahead of its main scientific objectives. The first of these rehearsal encounters happened in November of 2023, when Lucy flew past a small main belt asteroid called Dinkinesh, intended primarily as an engineering test of the spacecraft's innovative asteroid tracking navigation system. That test turned into a genuine scientific discovery almost immediately. As Lucy's cameras captured images during the flyby, mission scientists realized Dinkinesh was not traveling alone. It had a small companion, a tiny satellite asteroid the team later named Selim, after a separate famous hominin fossil sometimes referred to as Lucy's baby. Even more remarkably, subsequent analysis revealed Selim itself as what scientists call a contact binary, made up of 2 separate smaller bodies that had gently merged together over time, the very first asteroid satellite of this specific type ever confirmed by any spacecraft. If you are new here and love watching real space missions rack up unexpected discoveries along the way to their main objective, now would be a great time to hit that subscribe button, because there is a lot more of this waiting for you. Then, on April 20th, 2025, Lucy conducted its second major rehearsal flyby, passing within roughly 600 miles of a significantly larger main belt asteroid named Donaldjohanson, fittingly named after the paleoanthropologist who originally discovered the Lucy fossil back in 1974. The very first images beamed back from this encounter immediately caught researchers' attention, revealing an oddly elongated, distinctly lumpy shape that mission scientists quickly began comparing to a peanut. According to Hal Levison, the principal investigator for the Lucy mission at the Southwest Research Institute, Donaldjohanson displayed strikingly complicated geology, exactly the kind of detailed surface structure researchers hoped. Studying up close might reveal important information about the collisional processes that helped form the planets in our early solar system. More than a year later, in June of 2026, the full scientific analysis of that flyby was finally published in the journal Science, and the results turned out to be genuinely fascinating. Researchers determined that Donaldjohanson likely formed roughly 150 million years ago, when a much larger parent asteroid was violently broken apart in a massive collision, making it part of what astronomers call the Aragoni family, a group of asteroids sharing similar orbits that all trace back to that same ancient collisional event. Even more intriguing, the detailed shape and spin data gathered during the flyby revealed that Donaldjohanson has been slowly, continuously reshaped ever since that original collision, not by additional impacts, but by something called the Yorp effect, an extremely subtle but persistent force caused by sunlight itself gradually altering the asteroid's rotation and shape over millions of years. That detail matters enormously for planetary scientists because it demonstrates something genuinely important about how small bodies in our solar system evolve over enormous timescales. An asteroid does not need to experience another dramatic collision to keep changing shape and behavior. The simple, continuous pressure of sunlight, acting over millions of years, can meaningfully reshape and alter the spin of even a fairly substantial space rock, roughly 3 miles across, an effect too subtle to notice on any human timescale, but powerful enough to leave a clearly measurable signature once a spacecraft finally gets close enough to study it directly. Researchers studying Donaldjohanson have also pointed out something genuinely interesting about its broader context within the solar system. The Aragoni asteroid family that Donaldjohanson belongs to originated in the inner main asteroid belt, not particularly far from the source regions of 2 other well-studied asteroids, Bennu and Ryugu, both of which have already been directly visited and sampled by other missions, NASA's OSIRIS-REx and Japan's Hayabusa 2, respectively. Scientists studying Lucy's data on Donaldjohanson have noted that its characteristics appear quite distinct from both Bennu and Ryugu, even though all 3 objects share a broadly similar region of origin, a difference that researchers hope to better understand as they continue comparing data across all 3 missions. With both rehearsal flybys now successfully completed and thoroughly analyzed, Lucy's mission team has spent 2026 preparing intensively for the spacecraft's true primary objective, its first encounters with the Jupiter Trojan asteroids themselves. This spring, mission scientists began instructing Lucy to turn its high-resolution cameras toward 4 of its upcoming Trojan targets: Euripides, Polymele, Lucas, and Oris, capturing early test images from hundreds of millions of miles away, specifically to help the team fine-tune camera settings ahead of the real encounters. Even from that enormous distance, these future targets currently appear as little more to determine the quality of the historic close-up images Lucy eventually captures once it finally arrives. Those genuine encounters are now approaching quickly. Lucy is scheduled to fly past Euripides and its small companion moon, Keta, in August of 2027, followed by Polymele in September of that same year, Lucas in April of 2028, and Oris that following November, moving its speeds up to 16,000 miles per hour as it captures visible and infrared data during each individual pass. The mission's ultimate finale is scheduled for March of 2033, when Lucy will finally reach Patroclus and its near-twin, binary companion Menoetius, concluding a journey spanning more than a decade and covering distances almost impossible to properly visualize. It also helps to appreciate just how difficult it actually is to gather meaningful scientific data during an encounter this brief and this fast. When Lucy passed Donaldjohanson at more than 30,000 miles per hour, the spacecraft had only a narrow window of just a few minutes to capture every single image and measurement it would ever get of that asteroid, since Lucy has no ability to slow down, enter orbit, or return for a second Luke. Every camera angle, every instrument setting, and every precise moment of image capture had to be planned meticulously in advance, calculated using predicted trajectories that themselves relied on earlier, more distant observations of the asteroid's position and motion. A single miscalculation in timing could mean missing the asteroid's closest approach entirely, or capturing blurred, unusable images instead of the sharp, detailed data researchers actually needed. This is exactly why the earlier Dinkinesh flyby served such a valuable purpose as a genuine engineering rehearsal, rather than simply being a nice bonus discovery. Successfully tracking, photographing, and gathering usable data from a small, previously unstudied asteroid during a brief, high-speed pass gave the Lucy team invaluable real-world experience and confidence in their systems. But well before they needed to rely on those exact same systems for the mission's true primary objective. Discovering Selim, Dinkinesh's tiny satellite, during that rehearsal was a welcome scientific bonus, but the true purpose of that encounter was proving the spacecraft's asteroid tracking navigation system actually worked as designed under real-world conditions rather than just in laboratory simulations back on Earth. That same careful, methodical approach carried directly into the Donaldjohanson encounter as well. Because that flyby was explicitly treated as a dress rehearsal for the far more scientifically important Trojan asteroid encounters still to come, mission scientists used the opportunity to practice exactly the kind of instrument sequencing, camera slewing, and data downlink procedures they will eventually rely on when Lucy finally reaches Euripides, Polymele, Lucas, and Oris starting in 2027. Every Lesson learned from tracking Donaldjohanson's oddly shaped tumbling profile directly improves the team's confidence and precision heading into encounters with completely unknown, never-before photographed Trojan asteroids, where there will be even less room for error, given how much more scientifically consequential those primary encounters actually are. There is something worth appreciating, too, about just how much patience a mission like this genuinely requires, both from the spacecraft itself and from the scientists dedicating years of their careers to it. Lucy's team spent nearly 4 years traveling through space before conducting its very first meaningful asteroid encounter, and the mission's true centerpiece, the Trojan asteroid flybys, will not even begin until roughly 6 years after launch. By the time Lucy finally reaches its ultimate destination, Patroclus and Menoetius, in March of 2033, more than 11 years will have passed since the spacecraft first left Earth. Many of the graduate students and early career researchers currently working on this mission will have spent the majority of their professional careers waiting for this single spacecraft to reach its final, most scientifically significant targets, a level of sustained, delayed gratification that is genuinely rare outside of major space exploration projects like this one. That patience is exactly what makes ancient, unexplored objects like the Jupiter Trojans so scientifically valuable in the first place. Unlike planets, which have spent billions of years undergoing dramatic geological transformation, volcanic activity, and atmospheric change, small, cold, distant asteroids like the Trojans have remained comparatively unchanged since the earliest days of our solar system's formation. Studying them up close offers scientists something close to a genuine time capsule, a rare, largely unaltered glimpse into the raw building blocks and violent collisional processes that eventually assembled into the planets we know today, including Earth itself. No spacecraft has ever visited the Jupiter Trojan asteroids before, which means every single encounter still to come represents genuinely first-of-its-kind scientific exploration. If 2 relatively brief rehearsal flybys through the comparatively well-studied main asteroid belt could reveal discoveries significant enough to earn publication in one of the world's most prestigious scientific journals, the eventual scientific yield from Lucy's true primary mission, studying ancient, never-before-visited fossils from the earliest days of our solar system, promises to be extraordinary. If this story left you excited about everything still ahead for this remarkable patient mission, make sure you are subscribed with notifications turned on, because Lucy's real work is only just beginning, and there is a very good chance its first close encounter with a genuine Jupiter Trojan asteroid arriving in 2027 reveals something about the early solar system that nobody has ever seen up close before. It is also worth appreciating the sheer scale of collaboration required to keep a mission like this running successfully for over a decade. Lucy is led by Southwest Research Institute, with NASA's Goddard Space Flight Center managing overall mission operations, and Lockheed Martin Space, responsible for building and operating the spacecraft itself. Coordinating a mission spanning 12 years and 4 billion miles requires enormous institutional continuity, careful long-term planning, and a genuinely stable, well-funded commitment from NASA, since abandoning or significantly altering the mission partway through would waste years of already completed travel and preparation. That kind of sustained, multi-decade institutional commitment is relatively rare even within space exploration, making Lucy's steady, well-executed progress so far a genuinely notable achievement in its own right, independent of whatever specific scientific discoveries it eventually produces at its primary Trojan asteroid targets. After more than 4 billion miles of travel and years of careful preparation built on lessons learned from 2 remarkably successful rehearsal flybys, Lucy is finally approaching the moment its entire mission was actually designed for, and given everything this spacecraft has already managed to discover along the way, on nothing more than a couple of brief practice runs through the main asteroid belt, the wait genuinely seems worth it, and the best of this mission's science, the true reason Lucy was ever built in the first place, is still years away from actually arriving, quietly waiting somewhere out among the stars for Lucy to finally catch up to it.